Hello friends, today I will discuss the cogging and crawling in a three-phase induction motor. In this video, the definition of cogging, the definition of crawling will be discussed, and the reason for cogging and the reasons for crawling. Similarly, the solution for cogging are covered in this video. So in general, cogging means the stopping of rotation of the rotor in a three-phase induction motor. Crawling means slow movement of the rotor. So let me consider first cogging. The reason for cogging is, one is the ratio of stator slots to the rotor slot is an integer, means a whole number. The another reason is load torque is more than the motor torque. The solution for this are, number one is using the fractional ratio of stator slots to the rotor slots. The second solution is skewing the rotor slots. When the stator slots and rotor slots are same like this, here there are 12 stator slots, 12 rotor slots like this. In this case, here is the air gap between the stator and the rotor slots like this. And in the air gap, there is a reluctance, there is a flux that comes from the stator. The motor has a torque, operating torque, or in general torque. Let us say it has the capacity of 12 Newton meters. So let us say the load connected to the motor is 11 Newton meters. When there is a flux linking between the stator and the rotor slots, there is a magnetization here. Means they try to this cores, both the stator and rotor cores are magnetic materials. They try to lock each other. So means the rotor will not move. In a three-phase induction motor, the rotor speed must be a little bit less than the stator magnetic field speed. If you look at this, if the motor torque is 12 Newton meters and the load torque is 11 Newton meters, and there is a alignment torque between this rotor slots and the stator slots in the air gap, that is called alignment torque, and let us say that is equal to 1.5 Newton meters. So the motor to operate, the motor torque must be more than the load torque plus alignment torque, that is here 11 plus 1.5 means 12.5 Newton meters will become the load torque, whereas the motor torque is only 12 Newton meters. When the load torque is more than the motor torque, then the motor do not move. This is the reason when the ratio of the stator slots to the rotor slot is pure integer. Even if you take the stator slots 12 and rotor slots 6, then also this cogging problem cannot be avoided. Suppose the stator slots are 12 and rotor slots are 14. In that case, that will become fraction, and this alignment torque is going to nullify. Then the motor will run. There is another way of explaining this with respect to the graph. This is the load torque versus speed and slip. This is the original motor torque slip characteristic or torque speed characteristic, and this motor is supposed to operate at this speed, that is ns2, that is stable region. If the load torque, let us say TL1 is characteristic is like this, and this is the motor characteristic with the thick line. And if you look at this, the load torque is less than the motor torque when the speed is 0, that is slip is equal to 1. In this case, as the motor torque is more than the load torque, the motor speed increases like this, and it goes on like this, and it moves like this, and this load torque TL1 will cut this main torque slip characteristic here, and after this the load torque is more than the torque produced by the motor, that is motor torque. So here beyond the load torque point, the motor torque goes on reduces, whereas here the speed of the rotor is near to the NS2. This is NS2 and this is the near to the uh, synchronous speed. So as the torque reduces, automatically the motor decelerates. It comes back like this instead of going beyond it, and it will settle down here. This is called the stable operating point of the rotor of the three-phase induction motor. Suppose the load torque is like this, more than the motor torque. So in that case, there is no question of motor uh, moving the motor cannot run because the load torque is more than the motor torque. So the motor remains in the off position. So this is called the cogging or stopping of the rotor operation. To overcome this, so there is another solution called the skewing the rotor slots. This is the rotor of a squirrel cage induction motor, and these are the rotor slots, and in these rotor slots there are conductors like this. Earlier these rotor conductors were parallel to the rotor axis, but now it's not so. When the rotor slots are skewed, it can be drawn like this with the dark lines. Black lines indicates the skewing of the rotor slots, and whereas this red lines indicates the slots of rotor slot position imposed onto the rotor slots, stator slots imposed on the rotor slots, and the flux that is linking with from the stator to the rotor slots, that is from the air gap, is like this. If you look at this, this is the stator position like this, whereas this is the rotor slot. So here is the alignment force, and here is also alignment force, means alignment torque, and here is also alignment torque. This works in the one direction, whereas the other works in the other direction. Means this and this going to get cancelled, so that the rotor do not stop. Instead, it will move with the stator magnetic field as long as the load torque is less than the motor torque. Next, crawling. Crawling means it is the slow movement of the rotor or the motor running at very low speeds, that is less than the standard synchronous, near to the synchronous speed. The reason for this is space harmonics present in the air gap of the three-phase induction motor. If you look at the torque slip characteristics with the harmonics present in the space, so here is the characteristic of the three-phase induction motor. So this is the standard torque slip characteristics of three-phase induction motor, and from here to here it is called the motor mode or motor operation, and whereas from here to here this is called the braking mode of operation of the three-phase induction motor, whereas here from here to here this is called the generating mode, and in this region slip is less than 0, that is negative slip, whereas from here to here the slip is 0 to 1, and whereas here in this case braking mode the slip is more than 1. And in this, so there are harmonics present in the magnetic field, that is fundamental, fifth harmonic, seventh harmonic, like that. There are several harmonics present, and higher order harmonics more than seventh harmonic is neglected, and the magnitude of the harmonics is also less compared to the fundamental magnitude, and the speed of the seventh harmonic is standard synchronous speed by 7, and the sequence of the seventh harmonics is positive sequence, whereas the fifth harmonic sequence is negative sequence. That means the rotor magnetic field opposes the stator magnetic field direction, whereas in this region the stator magnetic field direction and the rotor magnetic field direction are one and the same. And once we consider seventh harmonic, this is the torque slip characteristic of the seventh harmonic, and this dotted line indicates the load torque. So when with the seventh harmonic torque slip characteristic, if we analyze it, so here the seventh harmonic torque at 0 speed is more than the load torque, so the motor will run, the motor rotor will move, and its torque goes on, speed increases and its torque also increases like this, and after some speed its torque reduces like this, and at this point, so this is the point where the motoring mode operation of the motor ends. So the motor reaches the torque at this point, and whereas the load torque is here, means the rotor can attain maximum speed up to here, that is ns by 7, and beyond this it cannot move, because beyond this the motor torque reduces, whereas the load torque remains like this. So as a result the motor decelerates and it will come back to this position. So the motor always operates below this ns by 7 speed, so somewhere here, means it cannot reach the normal synchronous, near to the synchronous speed. This is the standard synchronous speed, and its operating speed supposed to be here, means very near to the synchronous speed, whereas here due to the seventh harmonic and due to its motor mode operation ends here, so the motor will operate only at a speed near to the ns by 7, it's not near to the ns. Similarly is the fifth harmonic. So let me summarize. Once we have seen what is the definition of cogging, what is the definition of crawling, and we have seen what is the reason for the cogging and what are the solutions for the cogging. Similarly, we have seen what are the reasons for the crawling.